All right, so we're on to 3.5 rational functions and their graphs. Okay, so you'll want to recall rational is a fancy word for fraction. Okay, so we are going to graph these, but we have a lot to learn before we get to that point. So first, we're going to review on how to determine restricted values of the domain of these following functions here. And so these are rational functions, by the way. And so if you remember, restricted values are, you don't want to square root negative numbers, but we also do not want to divide by 0. So all you have to do is take the denominator and ask yourself, okay, what would make that equal 0? Because whatever does that, I don't want to include that value. And so right here, I can just add an x to both sides real quick, and I get 2 equals x, or x equals 2. And that's actually my restricted value, so I'm going to go ahead and put a slash through it saying we don't want to include that value. So you can plug in anything else you want into this function, but if you plug in a 2, we'll get undefined because we cannot divide by 0. Okay, on number 3, same idea. So we'll take the denominator and we'll set it equal to 0. We want to know what would make it equal 0, and we're going to stay away from that. And so this factors pretty easily into, let's see, x minus 5, x minus 1. And so those restricted values would be, we don't want x to be 5 or positive 1. Either one of those would cause the function to be undefined. Now, why is that important? It's because when we graph it, we can't graph those values. And so, anyways, it's just kind of a preview to kind of get us ready and a little bit of a review. Okay, so rational functions can be written in the form f of x equals n of x over d of x, numerator on top, denominator on bottom, as long as the denominator is not 0. And so that's what we just kind of talked about. So we're going to talk about the most basic one first, and we're really going to kind of take a deep dive. And as we get more comfortable with these, they move pretty quickly, but this first one I'm really going to drill down and really look at this real closely. So right here it says graph the function f of x equals 1 divided by x, and discuss the behavior of f near its excluded value, or values. In this case, we only have one excluded value, but you can have more than one. And as x becomes a large positive number, and as x becomes a large negative number. Okay. Well, typically if you're going to graph something, we typically just kind of make a table. So let's go ahead. I'm just going to start making a table, like I would with any function. I don't know. I'd maybe do like -3, -2, -1, 0, 1, 2, 3. So I'm just going to be pretty generic. And so I'm going to plug that in here. And so I'm going to get 1 over -3, 1 over -2, 1 over -1, which would simplify to -1, and then 1 over 0. Uh-oh, that's going to be undefined. Okay, so that's my restricted value. And then let's see, if I plug in a 1, 1 over 1, that's just a 1. 1 over 2, well, that's just 1 over 2, and then 1/3, and so on. Okay, interesting. So these numbers are pretty small, it looks like. As I get close to my undefined, it looks like it's starting to get a little bit larger. Interesting. Okay. Well, why don't we get even closer to my undefined? So I'm going to make another table over here, and we'll get a little bit closer. Like, what if I plug in, I'm going to stay on the positive side right now, but we can look at the negative side in a minute. But what if I plug in like a 1/2? Let's see what would happen. I'd have 1 over 1/2. And when I do keep, change, flip, I'd end up with 1 times 2, which is 2. Because I keep the numerator and then flip this. So this is really 2 over 1, but same thing, it's 2. And then you multiply. So that's keep, change it to multiplication, and then flip it. Okay, so 1/2. Okay. Let's get even closer. Let's see, how about 1/3? Well, 1 over 1/3, and it's going to be the same pattern here. It's going to become 1 times 3, which then is 3. So that's weird. I'm starting to get, my numbers are getting a little bit bigger. So what if I plug in like 1 over 10? And I'm sure you're seeing this pattern play out here. So change it to multiplication, then flip this, which 10 over 1 is just 10. And so I get a 10 there. So I'm getting pretty big now. So the closer and closer I get to 0 for my x value, because remember I can't do that because that's undefined, but I'm starting to get to a really large number. So like if I plug in 1 over 1,000, it's going to give me 1,000 in return, right? I'm assuming that we're seeing the pattern that's taking place, is that it's getting flipped, and basically it's the denominator that you can see right there. So if I get really close to 0, I'm getting really large. It's getting really large as I get closer to 0. Now, let's see, does the same thing happen if I plug in, negative numbers that are close to 0? Well, let's try like negative 1/5. Okay, so if I do negative 1/5, that'd be 1 over negative 1/5. And then it'd be change it to multiplication. Then when I flip that, the reciprocal of that is negative 5, right? If I flip that fraction, the reciprocal is negative 5. And I get negative 5. So the pattern holds that, basically I'm getting that denominator there. The only difference is now it's coming back as negative numbers, but they're getting larger. Okay, so I'm going to go ahead and kind of plot some of the numbers that we have so far, and then we can talk about this a little bit closer. So let's see, we'll do this in red. At negative 3, I was only at like 1/3. At negative 2, I'm at I'm sorry, I'm on the wrong side. Let's see, negative 3 and negative 1/3, then negative 1/2, and negative 1, I'm at negative 1. And then if I'm at negative 1/5, I'm all the way down here at negative 5 right there, right? Okay, let's see. On the other side, let's see, if I plug in 1/10, I'm way up here at 10, so I'm almost touching the y-axis right there. I'm at 1/10 over, and then I'm up 10 spots. And then let's see, if I go over 1/3, I'm going to go up 3 spots, which is about right there. And let's see, then let's plug in 1, 2, I get a half, 3, I get a third. Okay, so I'm going to go ahead and draw this, and then we can talk a little bit more about the behavior of this. So this doesn't touch the y-axis because that's where x equals 0. Remember, that's undefined. So I'm going to draw this. And then also, this doesn't touch the x-axis either. Okay, it doesn't touch the x-axis. It gets really close, but it doesn't actually touch it. And we'll talk about that too in a second. Now, on the other side thing, it's going to be a reflection right here across this diagonal line right here. It's going to be a reflection on the other side. And so this is going down, but it doesn't touch the y-axis. But it gets really close to it, but it won't touch it. Same thing, it curves up here, but won't touch the x-axis. It gets really close, okay? So that's the graph right there. But they're going to be a lot easier to graph as we get more comfortable with this. But this is generally how they're going to look. I mean, they can have a little quirks to it and stuff, but for the most part, we're going to stay fairly simple in here. But if you were to go on to pre-cal and stuff like that, they can get a little bit more interesting. But for the most part, ours are going to look pretty similar to this. We will have a couple where we have more than one restricted value, and so that would cause a couple schisms in the graph, okay? But let's look at that behavior. So here's the kind of the formal definition of what's going on here. If f of x is going to infinity or negative infinity at some value as x approaches some value a, then the line x equals a is a vertical asymptote. So I don't know if you've ever heard of asymptotes before, but we have a vertical asymptote right here, and it's the y-axis right here. It's the y-axis, and what's going on is as x is approaching 0, what's happening, it depends on what side you're approaching from. So sometimes you'll say as x approaches from 0 from the positive, you put a plus. What's happening here is that the function f of x, or basically the y value, is going to infinity, and that's what's happening on my right side. Okay, now all this stuff is pretty technical. I'm not going to require you to do the technical stuff. Really, you're just going to be required to graph, but I just want to go ahead and show you this. Now, as x approaches 0 from the negative side of it, or basically the left side, this time the function f of x is going towards negative infinity. So see, that's where it's diverging to, right here. The closer and closer I get to 0 from the left side, right here, my function diverges. So that's your vertical asymptote. So vertical asymptotes are pretty easy to find. They're just the restricted values of the domain, and those are going to help a lot when it comes time to graph these. They're going to make it a lot easier for us to graph these. If you notice, I plotted like 8 points. Once we get really comfortable with this, we're going to plot 2, maybe 4 points. You know, we're not going to plot a lot of points because the asymptotes are actually kind of like guardrails for us. So we have a vertical asymptote, and we actually also have horizontal asymptotes. And so looking at part 2 down here of our definitions, if my function approaches some value b as x goes to infinity or negative infinity, then the line y equals b is a horizontal asymptote. So what's going on in this particular example is our function approaches 0. It approaches 0 as x goes to infinity or negative infinity. As my numbers were getting bigger, so like if I were to plug in, let's say 100, then the return value would be 1 over 100, right? Or if I plug in, 1 billion, then it would be 1 over 1 billion, right? And so 1 over a billion is a very small number. So that's what's happening is x gets exponentially larger, either direction, positive or negative numbers, then the function may converge to a value. It's not always 0. This particular example is 0. So I have a horizontal asymptote right here going across, and actually let me see if I can use I guess I'm not going to do that. These aren't working well. Okay, so here we go. This is what I was thinking of. Here we go. Maybe we can see this a little bit better. There we go. There's my horizontal, and then there's my vertical asymptote. And so moving forward, when we start to graph these, we'll put those there so they can help us. They're going to be guardrails to help us graph it, so I don't have to find a million points. I only have to find 1 or 2, and then just kind of draw my graph with a curve. We just want to make sure there's a curve here. Okay, let's go ahead and move on. So let's talk about asymptotes of rational functions. Let f be a rational function given that f of x equals n of x divided by d of x, where n of x and d of x have no common factors. Okay, the graph of f has a vertical asymptote at the zeros of the d of x, which is the denominator, basically just the restricted values. Don't overthink this. Note, as long as n of x does not have the same zeros, that's something that would be covered in pre-calculus. So you don't even really need to worry about this note right here. That's not gonna be an issue for us. Okay, so vertical asymptote's pretty easy. Just find the restricted values. It's the restricted values. Those were how you find your vertical asymptotes. Horizontal asymptotes are a little different. And so there's actually 3 different things that can happen. We're actually really only going to focus on 2 of them, but I'm going to go ahead and mention all 3. So the graph f has 1 or no horizontal asymptotes determined by comparing the degrees of your numerator and your denominator. If the degree of the numerator is less than the degree of the denominator, the graph f has a line of y equals 0 as a horizontal asymptote. So this happens by default if the degree of the numerator is less than the degree of the denominator. So let me give you an example of that. So like if you had x plus, I don't know, 3 over x squared plus 2x, whatever. I'm just making something up. That right there would fall into the category of the numerator power being less than the denominator, because the numerator exponent, the highest power is 1, and then the denominator spot, the highest power is a 2. And so that's what you're comparing. That's what we're talking about. You're just comparing the highest power on top and bottom. And so if the power on top is smaller than the power on bottom, it automatically goes to y equals 0. Now, that should make sense, because if you think about it, if you were to plug into this function, if you were to plug in f of, whatever, and basically infinity, but what's going to happen is it's going to converge to 0, because what happens is, yeah, you have a huge number on top, right? You plug in whatever you want to plug in, trillion, whatever. But on bottom, you're squaring the trillion. And so when you square it, it makes the denominator so much bigger, okay? So what happens here is, even though the top might be a huge number, the bottom is going to be infinitely larger, and so that ratio would converge to 0. And so that's why you have a horizontal asymptote at 0 if the numerator power is smaller than the denominator power. Okay, so that's one thing that could happen. The other thing that could happen is, what if the degrees of the numerator and the denominator are equal? What if they're equal? Okay, well, then what you do is the horizontal asymptote will be the ratio of the leading coefficients. And so let me go ahead and show you an example of that. Okay, so for this example, let's see, let's do 2x plus 3 over, let's just say just x, whatever. Okay, so they have the same, and I could put it as a square, whatever. It doesn't really matter, as long as they have the same highest power, which they do, but they both have an x. Then what you do is you just take the ratio of the coefficients, which is 2 and 1. So that line would be y equals 2 over 1, or just basically y equals 2. Now, once again, that should make sense as the function goes to infinity, okay? So if you plug in f of infinity, or whatever you want to plug in, like a really large number, what's going to happen is you have twice as much on top, plus 3, which really, when we're talking about trillions and trillions and trillions, an extra 3 on top makes really no difference, right? So if we're talking about astronomically large numbers, if you add an extra 3, that doesn't really make much of a difference. But you can see that this right here would reduce down to a 2. That reduces down to a 2 right there. So that's kind of what's taking place right here. So if the powers, the highest power on top and the highest power on bottom, are the same, if they're the same, it could be power of 1, 2, 3, whatever, you just go ahead and take the ratio of the coefficients. All that other stuff, sure, it's important, but when you're talking about astronomically large numbers, it's basically a moot point at that, whenever you do that. Okay, the last one is, we actually aren't going to deal with in this course, but we'll go ahead and mention it. If the degree of a numerator is greater than the degree of a denominator, then the graph has no horizontal asymptote. So I'll give you an example of it, but then, like I said, that'd be something you would cover in a later class. So let's say that you had, 2x squared plus 3 over x minus 1, whatever. I just made it up real quick. So what's going on here is the power on top is larger than the power on bottom, and so you do not have a horizontal asymptote, okay? And so the issue here is that if you go to infinity, like if you plug in f of infinity, it's going to go to infinity also, okay? So there's no gap in the graph of the range, okay? And there's something else you deal with there, and I'm just going to kind of leave it at that. And so really we just need to worry about whenever the numerator power is less than the denominator power, and then when they're equal. All right, so now what we'll do is we're actually going to take a look at some of these pictures so we can see everything in action. So these are already done for us, but this is kind of helpful. You know, we don't want to jump right in and start graphing them. And so we can kind of examine the equation and kind of see where everything comes from. So if we look at our first one right here, we have g of x is equal to 3 divided by x minus 2. And so vertical asymptote is at x equals 2, okay? Because that's the restricted value, right? That's the value, you can't plug that in, you would divide by 0. That's where that comes from. Then to find the horizontal asymptote, we do the comparison test. And so the top one doesn't have a variable. Whenever you don't have a variable on top, it's there, but it has an understood power of 0. So the power on top is less than the power on bottom, so we default to y equals 0. And that should make sense, because if you plug in infinity, or like a super large number for x, basically it's going to converge to 0 right there. Now let's look at our next example. This time, let's see, the restricted value is going to be 0. So we have a vertical asymptote at x equals 0. Okay. And then let's see, the horizontal asymptote, you notice we do have variables with the same power. So we take the ratio of their coefficients. So it's going to be y equals 2 over 1, which equals 2. So y equals 2, that's the horizontal asymptote. Okay? And so whenever we start graphing these, what we'll do is we'll put the asymptotes on there, and then we're just going to test a couple points. You can see there's not a lot of points. They're using 3 points and graphing it, and that's what we're going to do also. So you're not going to have to find a million points like we did on the first example. Okay, so most of them are going to look like these first two. Usually they're diagonal of each other, the graphs, but not always. Sometimes they can be side by side, so just kind of be aware of that. But then sometimes we can have more than one vertical asymptote. And when that happens, we get one of these two graphs right here. One of these two graphs. So we'll look at each one of these. And so this first one, so if you take the denominator and we set it equal to 0 and factor, we're going to get x minus 2, x plus 1 equals 0. So our restricted values are 2 and negative 1, and that's where the vertical asymptotes are at. So we have vertical asymptotes right here and here. We got them listed. And then for the horizontal asymptote, you can see that the top power is smaller than the bottom power. So it defaults to y equals 0. All right. And then, so the difference on this one, though, is you're going to have something in the middle that either kind of looks cubic shaped or something that looks more like a parabola shape, okay? And so in this example, it ended up being a cubic shape. And so you have to find the 3 points to determine that. So we'll graph some of these in a moment, but we'll have to find 3 points. If you have two vertical asymptotes, make sure you find 3 points in the middle to figure out what kind of shape is it. Is it cubic, or is it more of that parabola shaped? I mean, it isn't those, but it kind of has that look to it. And then on the edges, you'll have to find an extra point also to figure out, make sure you're graphing in the right spot, and then use the asymptotes to help you from there. All right, so we got one more we can look at that we might run into. And so let's see. So once again, you can factor the denominator. And so we get our two vertical asymptotes are at -2 and +2. And we have those right here. Right here at x equals -2 and x equals +2. And then this time, the variables we have the same power. So you take the ratio here, so it's going to be 3 over 1. And then 3 divided by 1 is 3. So y equals 3. So there's that one. And then once again, you just, if you have two vertical asymptotes, find 3 points so you can figure out, is it kind of that parabola shape or is it more of a cubic shape? All right. So I think we're almost ready. I think we just want to practice and making sure we can find the asymptotes without a graph. So that's what we're going to do here. And then we'll be ready to start graphing. So find any horizontal asymptotes and vertical asymptotes, if there are any. So vertical asymptotes are the restricted values. So you just look at this denominator and be like, okay, yeah, x cannot equal negative 5. So that's the vertical asymptote. You don't have to put the not equals to because you're actually given the equation of the asymptote. Okay. The horizontal asymptote is where you take the ratio, right? And so I have x to the power of 1 on bottom. There is no x on top, so it hasn't understood x to the power of 0. So if the power on top is smaller than the power on bottom, it defaults to y equals 0. Okay, we have to be able to extract this information to graph these, or else there'll be a nightmare if we don't. Okay, the next one, the restricted value would be 1. So that's my vertical asymptote, x equals 1. Then the horizontal asymptote, you can see they're both the same power, so I will take the ratio this time. So y equals 3 over 1, or we'll just put it as y equals 3. And then the last one, it looks like we have 2 vertical asymptotes because this factors into x plus 2, x minus 2. So both positive and negative 2 are restricted. So my vertical asymptotes are at x equals negative 2 and x equals positive 2. And then for my horizontal asymptote, I can see that, yes, they have the same power. So I'm going to take the ratio. So it's going to be y equals negative 5 over 1, or just y equals negative 5. Okay, so this video is starting to get kind of long, so I'm going to go ahead and stop it here, and then I'll start a part 2, and we're ready to start graphing.